Okay, so let's move on. Our second speaker is Paul Heslop. Please.
Okay, thank you. Thank you very much for the invitation to speak here. It's great to be here in Taiwan in this wonderful venue and this great conference. I want to talk to you today about, as you can see, a number of works over the last 2.5 years or so. It's kind of two separate projects, if you like, all within the same umbrella. They're with Francesco Aquile, a postdoc in Milan, James Drummond in Southampton, and Enoch Paul. And since we're advertising people on the market, then Enoch Paul is a finishing PhD student who's absolutely brilliant. He's on the market at the moment. And then there's a separate work with some people in Durham, so Arthur Lipstein in Durham and student 2 to 8. Okay, and so it's about trying to explore quantum gravity from conformal bootstrap type ideas. Okay, so what are the big questions we're interested in? Well, two big questions are: what is quantum gravity? How do we complete a general relativistic theory to a UV complete theory? And how do we calculate things in quantum field theory? And as we all know, over the last 25 years or so, there's been two major developments that help to answer or partly answer these questions. So the first one is ADS-CFT, which tells us that quantum gravity is equal in certain cases to a quantum field theory, or more specifically, conformal field theory. And the second big idea is the conformal bootstrap, which is really an old idea that had a new lease of life in the last 10 or 15 years or so. And there's a very beautiful idea that you just define your conformal field theory by the spectrum, anomalous dimensions of operators and so on. That's your data together with 3-point functions, or the OPE coefficients. And then everything else can be, in principle, determined from those. And all other correlation functions can be built from them. In particular, the 4-point functions can be built from them. But of course, they have to satisfy a crossing symmetry, which schematically looks like this. When you do a block decomposition, you can do it in two different ways, and you have to get the same answer. So there's an infinite sum over all primaries, and different infinite sum over all primaries. They have to be equal. And the point is, this has to be true for all possible operators, all possible 4 operators. And the idea is that defines a CFT for you. Just write down data, with some unitary bounds, write down some 3-point functions, and then insist that it satisfies this, and then that defines for you a CFT. So anyway, there's the idea of this kind of program, and there's lots of other people doing similar things, is to simply use the CFT bootstrap ideas to help understand quantum gravity via the ADS-CFT correspondence. And in some sense, this is seminal work, kind of, if you like, along these ideas. Now, they gave a kind of a general picture with toy models of scalars, and I guess the difference with what we're doing is we're trying to use this in a very precise way to do particular computations in specific theories, namely the theories that are most the kind of canonical theories for ADS-CFT, namely n equals 4 super Yang-Mills, and then also a little bit I'll talk about the M theory versions. Okay, so in ADS-CFT, on the one hand you have a gravitational theory, and then when thinking of quantum gravity, you're expanding in G Newton, which on the CFT side becomes 1 over n squared, or central charge more generally, where n in the case of n equals 4 young males, is the gauge. And then also on the gravity side, you then, well, generically you would have an energy cutoff. And if you're specifically talking about string theory, this is taken by alpha prime. And that's related to a coupling in the CFT, the top coupling n equals 4. Now normally one would understand the ADS-CFT correspondence in this direction. You would say, well, I might understand gravity perturbatively. I can compute things for small g Newton and expanding in alpha prime for small string coupling, and then that should give me non-trivial information about my CFT at large coupling and large n, which otherwise would be hard to get. But then the bootstrap sort of idea turns that round on its head. So instead, using OP consistency really, which is what I mean by bootstrap ideas here. In fact, you can compute strong coupling results in CFT by themselves, using some kind of limited information that you know about from holography, but within, well, basically to do with the spectrum. And then that can actually give you perturbative computations in gravity, which, well, so far haven't been done directly on the gravitational. Okay, so a bit more specifically then, I'll be looking at these two theories, with the standard ADS-CFT correspondence is there. And I'll be using the bootstrap to get new results in quantum gravity. And in particular, I'll be looking at in the first part at tree-level terms, but sort of stringy tree-level terms, or the analogue of that in M theory. In particular, we'll be recovering the effect of the Arctic 4 term in the effective action for the 4-point functions. So that'll be the first part, and that's actually relatively, relatively straightforward to do once it's all set up. And then in the second half, I'm going to talk about. So here I'll be discussing that in M theory. Then I'll go back to n equals 4 young males, and I'll talk about doing a quantum gravity 1 loop calculation. So that's a 1 over n to the 4th calculation from the n equals 4 side. Purely from the CFT point of view. So this would correspond, if someone would do it, it would correspond to a loop calculation on the gravity side. But ADS loop calculations are very difficult, so nobody's done that. Along the way, actually, as we see, to get this, we need to do some unmixing, and we get a lot of precision data for operators. In particular, we'll get anomalous dimensions of all 2 particle states. I'll define this in a moment. So, roughly speaking, binding energies are bound 2 gravitational states, and they're 3 to leading order. Okay, so as a quick slide on ADS-CFT in the n equals 4 super young males side. So basically I'll only be really using or showing you scalars. So there are 6 scalars in the theory, and they're in the adjoint representation of SUN. So that's the particle structure on that side. On the other side, on the gravity side, of course, you've got a graviton and then all his supersymmetric partners in 10 dimensions. And then, of course, in principle, you've got string states. But in the limit that we're looking at, the gravity limit, the string states are going to be infinitely massive, or above the cutoff scale. So we can ignore those. And there's a correspondence between the states on this side and the operators in n equals 4 super young males. And this is how it goes. On the graviton, in 10 dimensions, we have to sort of compactify everything down to 5 dimensions. So you get a whole slew of Kaluza-Klein modes. And they just correspond to the following operators that I'm calling O2, just the trace of phi phi. in a certain representation, or a trace of p of these scalars. These are often called single trace operators, although you actually have to be a bit more precise because we're going down in 1 over n. There are corrections to this single trace. Anyway, so these are called, I'm going to call these single particle operators, and they're the basic building blocks. And then all the only other operators that you see are essentially products of these. OP times OP with various derivatives in between. So you can have symmetride derivatives or Laplacians. And these, roughly speaking, correspond to two particle graviton bound states. So these are actually the only operators I'll be considering in this talk. Of course, there are many other operators in n equals 4 Yang-Mills, but they either correspond to stringy states, which, as I said, we won't see them, or they correspond, or you can have higher point, you can have 3 particle states instead of just 2 particle states. And I can ignore these at the order that I'm looking at, but I can't ignore these forever. So these are basically suppressed by higher orders than 1 over n. But if we keep going, we need to take triple trace operators into account. But at the moment, I can ignore them. Okay, so I'll be looking at 4-point functions, and I was sort of exploring the kind of quantum gravity and string expansion directly from the bootstrap idea. So let me talk a little bit about why, for the purpose of this talk, why the fact that I have CFT dual, why that's useful, how I can get information from that. So you have an OPE. I mean, this is the main formula here, which this is the formula corresponding to the diagram I drew before of the block decomposition. So a 4-point function can be written as a sum over primary operators of some coefficients, which are essentially 3-point functions squared, times something called a conformal block. And these are essentially known objects. So this is it's really like a Taylor expansion. You give me a function, and I can Taylor expand it, or you give me a function, I can block expand it, and then read off these coefficients. Now, actually, the only important thing I need for the first part is that this tells you about the small u behavior of the 4-point function. So u is the cross ratio, and small u corresponds to the OPE limit. And so I have a certain power of u that my 4-point function behaves as when u goes to 0. Because this is the dimension of the operator appearing here, and they dimensions are not bounded. So, for example, this is a kind of just a toy example to give you a flavour. I write my 4-point function in terms of a function of 2 cross ratios, g of u and v. It has to be invariant under crossing symmetry, which is just permutations of these things, which becomes some transformation of u and v. U goes to 1 over u in particular is the key one there. So roughly speaking, if my function has to be invariant, then u goes to 1 over u, but it also has to have a certain minimal power of u, then that gives you constraints on the sorts of functions that can appear immediately. I can't have, for example, a polynomial function, which I use the a, b to the b, and you plug it in, then I cannot have a function which is of order u squared, which it turns out that I will want. So, I mean, physics gets around this, but of course, by using a particular type of function, which is essentially a polynomial divided by a certain denominator times logarithms, times polylogarithms. And the denominator allows you to get around the problem of crossing symmetry, but it introduces a new problem in that I am not supposed to have a pole for that denominator. And then then the challenge is to kill the pole by having zeros in the numerator. So the set of functions at tree level I'm only allowed polylogarithms of weight 2 and below. And the set of functions that are used are called D-bar functions. And they're just contact contact Witten diagram. I'll show you a bit more explicitly what these look like a bit later. Anyway, so I'm wanting to look at this correlator, and it has the following expansion. It's got an expansion in n, and or g Newton if you like, and in alpha prime, or lambda, 1 over lambda. And it has the following form: 1 over n squared, 1 over n to the 4, alpha prime cubed over n squared. And I want to try and sort of reproduce some of these things from bootstrap ideas. In particular, first I'll look at this correction here. So how could I derive this? This is not me, by the way. This was done by Aldane, Fissi, and Nikowski. Well, there's different ways of looking at the derivation. My preferred way is to say I know in advance the set of functions that should be written in terms of d-bars. I know in advance that the correlation function has to be of order u squared at small u. And then I just write down an arbitrary d-bar function, essentially, plus crossing. I have to use crossing symmetry. And then I insist that it's of order u squared. And then that gives you bounds on a, b, p, q, r, and s, because you know what these functions look like at small u. And in fact, the bound is as follows: p plus q plus r plus s has to be greater than or equal to 16. And then there's some bound on a and b as well. And then the minimal case, therefore, is when all of these things are 4. So you immediately see that within this class of functions, within this constraint of the correlation function, then there's a minimal case, which is this d-bar 4, 4, 4, 4. And that indeed is the answer. Now, so all that tells you is that this d-bar 4, 4 is a function which has the right properties. In fact, there are many functions that have the right properties, because this is just the minimal case. But then the work of Polczynski and collaborators showed you that you can actually examine a function and a term that appears in the effective action, and you can analyze its large twist behavior in the OPE. I don't have time to go into the details here, but that basically tells you the dimension of the coupling. So you can actually read off from the form of the function what dimension should be sitting here. Okay, now so this was done a while ago, and I like to kind of draw this plot of 2 parameters. So we've got g Newton, or 1 over n squared, expansion this way. So this is kind of like a quantum gravity expansion. And then this is the string expansion. And at the moment, I'm looking, we have tree-level supergravity, which is known, and I'm sort of trying to look at these directions. And this is the d-bar 4, 4, 4 that we just derived. And then the non-minimal cases give you further terms. So there's an infinite tower here, but the functions that appear, you can derive in the way I just described, and you know the power of alpha prime effectively as well. You don't know the coefficient in front of us, so if someone else has to fix for you the precise coefficient, you know the power of alpha prime. Okay, and then just to highlight, in a second I'm going to start looking at the loop corrections, which is a big deal. Now, if you're interested in M theory rather than string theory, then M theory, so I'm going to recast my string theory, because string theory, you might say I should really be expanding in G string and alpha prime rather than G Newton. So from a string theory point of view, these are lines of fixed alpha prime power and varying G string. And actually, this r to the 4 correction appears both as a tree level alpha prime q correction, but it also, the same r to the 4 appears as a supergravity counter term. So again, in quantum gravity point of view, this would be a one-loop quantum gravity result, and this would be a counter term, a sort of a divergent part down here. But string theory tells you that that has to be the exact same r to the 4 term, and it's given by this d bar 4, 4, 4, 4. So the same function appears here and here, and in fact, you see this r to the 4 multiplied by a function of G string, a kind of SL2Z covariant function. If people are familiar with those, it might be green or so on. Analyzes these things. So these appear as part of that expansion. Now, I want to look at M theory now, and M theory, there's no G string, so people would like to think of it as a G string as being 1, but I think it's maybe better to think of it as these lines kind of collapsed into 1. So it's like string theory, but with these the equivalence classes along these lines. So you only have this direction. And that's what I want to, basically now I want to reproduce what I just did for M theory. Okay, maybe I'll, well, you can stare at this slide, but again, it's the same, everything looks very much the same. Now we don't have a microscopic picture here, we don't have a gauge group or anything, but on this side, we know what gravity looks like, 11-dimensional supergravity, and therefore you can sort of read off what operators I must have in the supergravity limit of M theory. And then everything looks very similar, in fact, to the string theory case, the N equals 40 Mills case. This is 62.0. And the expansion looks very similar as well. But now I don't have an alpha prime cube. I only have, an M theory with only, there's no G string. So I have a 1 over n cubed, I have a 1 over n to the 6. These are my quantum gravity loops. And then I look for something that I want to be the analog of the tree string correction. And so I can play the same sort of game. I can look at I can look at functions of this form with d bars. And now there's a slightly more subtle constraint on the log u power, it turns out. The log u part has to be order u squared, but the non-log u part has to be of order u. And that's to do, for the experts, that's to do with non-renormalization of 3-point functions, which you have in N equals 4 Young-Mills, but you don't have here. So you can get some lower operators do have a correction in the analytic part. Even though they have no enormous dimension, their 3-point functions can be corrected. So anyway, if it wasn't for this, the setup would be the same as before, and I would end up with d bar 4, 4, 4, 4. But because of this difference, instead you end up with a different d bar function. And then you can analyze, you can then do an OPE, a block decomposition of this, find out the corresponding enormous dimensions, look at the large twist behavior, which, as I said before, gives you information about the number of, about the dimension, corresponding dimension of the term in the effective action. And in that way, you can deduce that this term has to be of order n to the minus 5. It has to come with L Planck 1 over n squared compared to the supergravity term. So again, that's the tree level supergravity. It's 1 over n cubed. G Newton is 1 over n cubed there. And then I need another 1 over n squared to get to here. So actually, it's the first correction. It comes before the 1 over correction. But the structure is very similar to string theory. It's just that you don't have this extra parameter, but but the functions have very close analogs with string theory. Again, I can't fix the coefficients using this method, so you need another method to fix the coefficient in front of you. And one such method is to try and use W algebra. Okay, so that was the first part to do with the effective action of of M theory. And now the second part is to try and deduce the one loop quantum gravity term in 2B supergravity from n equals 4 Yang-Mills bootstrap ideas. But again, it's just using the OPE, really. So I'll try and give you the key point in a second. But here is, in order n to the 0, on the gravity side we have 3 Witten diagrams. Order 1 over n squared, we have tree-level Witten diagrams. And now we want to bootstrap the loop Witten diagram, the order 1 over n to the 4 from these. Right, now this slide simply comes from the previous, the basic block decomposition here. Now this is non-perturbative, so everything here in principle can depend on the coupling. In particular, this delta here depends on the coupling. And now I just expand this perturbatively in the coupling. So this is u to the delta, which is e to the log, e to the delta log u. So if I expand it in the coupling, the anomalous dimension has a coupling in front of it. The only term, the leading log term, always comes with the first anomalous dimension, correction for the anomalous dimension. So you can see that's just expanding e to the anomalous dimension log u. So that's what I'm doing here. I hope that's good. This is the main point that allows everything to work in this part to get to one loop answer. So a to the 0, if I switch off the coupling, I just have essentially the same function, c2 to o squared, tree-level 3-point free theory 3-point functions. This is the free theory correlator. Then the tree-level correlator is given by this formula. It's got a log u term which has the anomalous dimension and the free theory 3-point functions. And then it's got some no log u terms. Right? I just want to focus on the log u term here. And now at next order, so this would be the one loop correlator. This is what I want to try and deduce, or bootstrap. Again, there's a term that has a log squared u in it. And that term has to come with c squared anomalous dimension squared. But this is this anomalous dimension. It's exactly the same eta as there. Eta squared, c squared, times log squared u. And then of course there's other terms with log u and no log term, and they have kind of new data. But the log squared u part only contains data from tree level and from free theory. So if you know the data here, in principle I can put it in and obtain the full log squared u part of the one loop correlation function. So that's the game we're playing. The idea is very simple. Because the detail, the devil's in the details, so it's quite technical to do this in practice. And more importantly, I can't just do this using this correlator. And it's because there's a sum here. There's more than one operator with the same free theory quantum numbers. So if there wasn't a sum here, I could literally just take the data from here and the data from here and obtain the data here. But because there's a sum over operators, I need more information. But that information still comes from tree level and free theory, but from more general correlators. So, okay, let me just try and very explicitly show you that in the case of twist 6. So twist is the dimension here. So there are two operators, there are two multiplets. These are both superprimaries with the same dimension. So this is O3, O3, so that's like roughly speaking dimension 6, and O2, Laplacian O2, that's also dimension 6. So these are the same quantum numbers, two of them. And so from doing this super block decomposition here, I only obtain the sum of, I get c squared plus c squared and c squared eta plus c squared eta. And then these I read off by doing my block decomposition of the tree level correlators. But this gives me two equations for four unknowns. And the way out is to consider more general correlators, again at tree level and in the free theory. Then I end up with 6 equations in total, so 2 here, and these 2. I get some more unknowns, but only 2 more unknowns. So I get 6 equations, 6 unknowns, and the system is perfect. It's perfectly solvable. And then that continues to higher twists. So I get some equations. I read them off using the superblock expansion. I solve them, and in this case, the twist 6 case, I get the following data. These are the anomalous dimensions. Now, remarkably, they're rational. Really, they shouldn't be, because these are essentially eigenvalues of a 2x2 matrix. So they shouldn't be rational. In general, generically, they shouldn't be rational, but they are. So that smells of something special going on. And then the C's are also special. They're square roots of rational. Okay, so this is the essence of what we're doing. Now there's a long story now where we analyse lots of correlations, lots of block decompositions, lots of unmixing to get the analogues of these for higher and higher twist data and more general representations. But the outcome is that once you've got enough data, you can sort of obtain a formula. I mean, this is really guessed at that, I guess. You get lots of data, and then eventually you spot a pattern and find a formula. So this again is the anomalous dimension of any 2-particle operator. So there you've got to have all the SU4 representations. So it's got twist, spin, and SU4F. So there's many quantum numbers, and this is the anomalous dimension. And there's some degeneracy there. It doesn't depend on Q here, only depends on P. So there's a number of operators that not only have the same free theory anomalous dimension, but also the same next order anomalous dimension. And this degeneracy has since been explained by Simon, who finds some kind of weird 10D conformal symmetry. And basically he says that all the single particle operators I've been discussing really fall into a single 10D massless field. And then all the double trace operators I'm now talking about here are therefore bilinears. They're essentially higher spin currents in 10 dimensions. There's one for each spin. And really I should think of this as the spin of this higher operator when you decompose it down into you're basically looking at SO2, 10 goes to SO2, 4 times SO6. Okay, well there isn't much time left. Now I haven't got to the key point yet, so I need to do that. The key point is I've got this data now. So I have the anomalous dimensions, beta, I have the C's, I have them all analytically by doing the unmixing. So now I can put it back into the formula for my one-loop correlator at order log squared u. So we have all this data analytically. I can therefore sum this to arbitrarily high order and obtain an expanded form for the function, which I then match with a particular ansatz. And now the ansatz is a very natural one, given what I sort of said in words earlier about the form of the d-bar functions. Everything at tree level in this holographic world has the following form: polynomial times weight 2 and below polylogs divided by x minus x bar to some power, where x and x bar are just some cross ratios. It's such that it's non-singular when x is equal to x bar. So this thing has to cleverly have zeros, many zeros in the limit x goes to x bar in order to cancel this. So I basically we use an ansatz of a similar form for the. You would now expect, because of a one higher order in perturbation theory, like from an amplitude point of view, you expect weight 4 polylogs now. Because that's how it works for conservatively. So, but this here we're looking at log squared u part. So for the log squared u part, you look at weight 2 polylogs. So you try and match an ansatz like this, where n can in principle be any power. And you find that it works for n equals 15 and for certain values of these polynomials. So we find precisely the full log squared u part of the one loop correlation function. And now the goal is then to lift that to the full function. So again we use an ansatz of a similar form, but now with weight 4 polylogical length. And this ansatz has to satisfy the following requirements. Well, first of all, the log squared u part, if I take log squared u of this, it has to equal what I got before. Okay. Secondly, it has to be finite as x goes to x bar, which puts a lot of constraints on these things. And also it has to be crossing symmetry invariant. And it turns out that under those requirements, you end up with well, it's unique up to one free parameter. And that free parameter is again this d bar 4444, which actually is not surprising once you realise that that's the one loop parameter. And since then, these have been fixed by Schleifer-Chesterton using localization, and so we now have a full one loop continuity force. Okay, good. Since then we've done things for higher charges, and we've looked at this sort of 10D symmetry by pulling out the delta 8. But well, if anyone wants to ask me questions about that, I can talk about that. Okay, here's a list of future work. I mean, higher loops, higher points. A sort of a completely orthogonal thing is the single particle half BPS operator you have to get right. It's not trace of phi to the 4, it's a correction. And we have a sort of a way of defining these as being the operators orthogonal to multi-particle operators, which gives an all-n definition, which is a really nice new basis for operators in n equals 4. String corrections, and M theory, obviously trying to do the loop, what I just did for n equals 4 in M theory would be also superblocks are interesting. There's a very nice mathematical relation. Okay, thank you.
I have a naive, perhaps tangential question. Do you think this bootstrap program would allow us to determine the structure of the effective action of string theory with false supercharges, in particular terms that are more leading than out to the fourth term?
More leading?
So like out square out. In principle, I don't know how to argue that they should not be there.
Oh, I see. Well, if you can come up with a well, I mean, I suppose all you really need is the states. You know, if you can come up with a conformal field theory joule, you don't really need to know much about the joule. You only need to know the spectrum on the gravity side. And then you could see how far you could go with it. I mean,
yeah, I could live with an ADS vacuum, so
yeah.
We should have it.
Yeah, no, I still have an ADS vacuum.
Yeah, but even then, I think some people argue that the leading correction is out to the law. You also consider like, why is this the case? We'll be able to check it.
Well, actually, these techniques will only maybe give you structure. If it's not there for some structural reason, then okay. But I mean, for example, in M theory, there are some corrections, not, or maybe even that one. There are some corrections which are there, which structurally can be there, but they have zero coefficient for some other reason. And this, the level I've spoken about, doesn't tell you about those things.
One question?
Yeah, it's also related that, so, I mean, can you get, like, at least formally write, for example, what exactly is the R4 coefficient just from the bootstrap equation? I mean, like,
not along the lines that I was just talking about. No, it's the functional form of the, because all I did was look at I looked at what functions you can write down, basically, that satisfy certain requirements. But you can always, all my requirements are homogeneous, so to speak. So to fix the R to the 4, yeah, I mean, they're all there's various ways that people do it, but I think not really a bootstrappy way. So you can relate it to flux space, you can do localization, but I think, what can I say about that? Yeah.
Like if you have the 4-point function, if I give you the solution to the crossing equation, can I get like what is the R4 of the effective theory and ADS, the coefficient of that R4? I'm asking because then we can talk about F-4, which would be talking about 4 current correlator. So we can look at 4 current correlator, and if I can identify F4, then I go back to the crossing equation and see if there's somehow some positivity found from the crossing equation that forces the F4 that particular sign.
Right.
So I was wondering, is there a way to just directly get that effective?
Well, you're just asking if I know the coefficient.
If I know the 4-point function.
If you know the 4-point function, you're asking, can you read up?
Yeah.
Well, I mean, I guess someone has to do the work. I mean, in principle, yeah. In practice, no. I mean, it's just working out the details of how to go from R to the 4 in ADS5 plus S5 to the boundary and relate it to the fulcrum. Along the way, there can be some coefficient that appears that you have to work out carefully.
So about since you have the log U expansion, so is there an understanding of what the discontinuity of the log U actually corresponds to? And when you write down the block, or when you have the 4-point function, and I look at the discontinuity, you have log U and you have double log U and this expansion. So if I look at these discontinuities, is there an understanding of the CFT side what this should correspond to?
I mean, I kind of showed you that.
So it's just the tree. So the CFT tells you that it should be that like the one loop should be the log U discontinuity is just the tree.
Yeah.
And so this will be a general feature.
Yeah, that's just basic sort of CFT of the statement. The leading log has to be at this form c² times eta. So
on the ADS side, is there also, do you need is that mismatched to the ADS side? So is there interpretation of this log in terms of written diagrams?
Yeah, I mean, there is this the story of Zeeman about the leading discontinuity. So he has some nice story there. Yeah, I'm not sure that it's really.
So that's an ADS.
Well, no, that's really a CFT. I mean, it doesn't say anything about ADS.
Okay, well, since we're already late today, so let's better move on to the next speaker. So let's thank Luis.